Welcome. Today we shall have the first tutorial of module 4, that is design of separation processes. In the theory lectures we have seen various kind of separation processes applied in chemical industry: distillation, absorption, adsorption, crystallization, liquid-liquid extraction, membrane processes, etc. We also saw under what criteria processes are selected, and now in the tutorial we shall see some problems based on these processes. Among all processes that are applied, the most common processes which are applied almost in every chemical industry, whether medium scale or large scale, are absorption and distillation. So, in the tutorial we shall mainly focus on these two processes. So, today we shall have the tutorial on absorption. Now, let us see the first problem of the tutorial. The problem statement is on your screen. A packed absorption tower is to be designed for removal of sulfur dioxide from gas exhaust, a mixture of air and SO2 of a plant. The design parameters are concentration of sulfur dioxide in the inlet gas stream 10 mole %. The desired removal of SO2 is 99%. Inlet gas stream flow rate, which is air plus SO2, is 33 meter cube per second. Temperature of the gas stream is 400 Kelvin, pressure of 111 kilopascals. Average molecular weight of gas stream is 29.1 kg per kilomole. Number of transfer units NTU are a function of the superficial velocity through superficial gas velocity through the tower Gs, and NTU is equal to Gs raised to 0.5. Now, this superficial gas velocity is based on cross sectional area of empty tower. The height of transfer unit HTU is 4.5 meters. The installed cost of tower, the fixed cost, is a function of tower volume as rupees 5,000 per meter cube. The annual fixed charges including depreciation are 20% of the installed cost. Operating cost of the tower given in rupees per second is a function of again the superficial gas velocity Gs as 0.001 Gs square plus 0.1 by Gs. The total operating time is estimated at 8,000 hour per year. For this design we have to determine the following parameters at conditions of minimum total annualized cost. First, the diameter of the tower D optimum, the height of the tower H optimum, superficial gas velocity at optimum condition Gs opt, and total annualized cost TAC in rupees per year, and total operating cost again in rupees per year. So, we start the solution. We have been given the flow rate of gas in meter cube per second. We first convert it into kg per meter square per second, the superficial gas velocity. The mass flow rate of gas is by simple relation. We assume ideal gas law to follow. 22.4 liters is the volume of 1 gram mole of gas at STP condition, 101.3 kilopascal and 273 Kelvin temperature. FV is the flow rate of gas in meter cube per second, and MW is the molecular weight. So, we substitute all values here. The mass flow rate of the gas, that we denote by Fm. Fm is equal to 1 by 22.4 into 111 by 101.3 into 273 by 400 into 33 into 29.1, and this turns out to be 32.06 kgs per second. We denote the diameter of the tower by letter capital D. So, the cross sectional area is pi d square by 4, and then Gs becomes 32.06 divided by pi by 4 d square, or after simplification this becomes 40.744 by d square kg per meter square per second. The height of the tower. Height of the tower that we denote by letter Z is HTU, height of transfer unit, into number of transfer unit, NTU. HTU has been given to us as 4.5 meter. NTU, number of transfer units, are a function of GS. GS raised to 0.5. So, the total height of the tower Z is 4.5 into GS raised to 0.5. We now substitute the expression that we derived for GS just now, 4.5 into Fm by pi by 4 d square raised to 0.5, and after substituting for Fm and simplifying, we get this as 28.75 divided by d. So, that is the height of the tower in terms of diameter of the tower. Now, the volume of the tower. Volume of the tower is cross sectional area into the height, which we write in terms of HTU and NTU. So, this is pi by 4 d square into 4.5 into Fm by pi by 4 d square raised to 0.5. And now, after substituting all values, we get this, and then after simplification it gives 22.58 into d, that is the volume of the tower in terms of diameter. The installed cost of tower or fixed cost is volume of tower multiplied by the unit cost, 5000 rupees per meter cube. So, 22.58 into d into 5000, that turns out to be 112,900 d. This is the total annualized capital cost, sorry, this is a total fixed cost. Now, we have to calculate the total annualized capital cost, and therefore, we have to annualize this particular installed fixed cost. Okay. So, to annualize the fixed capital cost, we shall use the capital recovery factor, which some books have also called as capital charge factor. And the typical value of this factor is 1 by 3. Capital charge factor is the acronym that we are going to use, CCF, and the typical value of this is 1 by 3. We shall deal with these things in greater detail in module 8 when we shall see the project economics. There are always two types of cost associated with every equipment. The first cost is the fixed cost or the capital cost for the equipment, and second is the operating cost. The fixed or capital cost is a single time cost, and the operating cost is a recurring cost. So, when we try to find out the total annualized capital cost, we have to convert the single time cost, that fixed cost, fixed capital cost, to a recurring basis cost, and then this particular factor, capital charge factor, is used for multiplication, for converting the capital cost to annualized cost. Okay. So, we shall see these things in greater detail in module 8. For time being, you can take these values for granted. Okay. So, the annualized capital cost is 1 by 3 of 112900 D, that is 37633.3 into D. The annual fixed charges are 20% of the capital cost. So, 0.2 into 112900 D, that is 22580 D. The annual variable or operating cost is 0.001 GS square plus 0.1 by GS. This is rupees per second. We are given 8000 hours of operation. So, into 8000 into 3600. Okay. So, now you substitute for GS here, substituting for GS and simplifying, gives GS we have already determined here as 28.75 divided by, or no, GS is determined as 40.744 divided by D square. So, that value you have to substitute here and then simplify. I am giving you the final answer. Simplification I am leaving as an exercise. 28800 GS square plus 28800 into GS and then so that is the annualized annual variable in operating cost. Now, the total annualized cost is the sum of annualized capital cost or annualized fixed cost plus the annual operating cost plus the annual fixed charges. So, now we substitute for all three cost that we have just derived. Total annualized cost is 37,633.33 into D plus 22580 into D plus the variable cost that we just determined 47,810,117.8 by D raised to 4 plus 70,685.25 D square. Okay. Now, for minimization of TAC, we take partial derivative with respect to D. So, D TAC by DD. Okay. So, this turns out to be 3733.3 plus 22580 minus 4 by D raised to 5 into 478.10117.8 plus 141,370.5 into d, and this we have to equate to 0. Then further simplification gives 60213 d raised to 5 minus 191,240,472 plus 141,370.5 d to the power 6, that is equal to 0. Now, we have basically polynomial in terms of d, we have to find out its roots. So, the best way is to use a numerical method. Okay. The simplest method is the Newton-Raphson method. For solution of above equation, numerical method may be used. For example, the simplest method is Newton-Raphson method. Newton-Raphson method subroutine is available in all simple softwares like MATLAB or Polymath or Maple. Okay. So, you can very easily put this equation, give a guess, let us say guess of 1 or 2 or 3, d is equal to 1 or 2 or 3, and then you can get a solution. So, I have done it, and then I have solved it with Newton-Raphson method. Solving with Newton-Raphson method, we get the optimum diameter d opt for minimum total annualized cost as 3.2582 meters. Okay. Now, I have taken 4 decimals for accuracy, you can even terminate at 2. So, 3.26 meters can or 3.3 meters, so forth. Okay. Now, having obtained value of d opt, we can estimate all costs and other parameters. And now I am giving the answers. First is h opt, height of the tower at optimum condition, that is 28.75 divided by d. So, substituting d, we get this as 8.824 meters. Then GS opt, it is 40.744 by d square, and again putting d equal to 3.2582, this comes out to be 3.838 kg per meter square per second. The total annualized cost turns out to be rupees 1.3708 into 10 to power 6 or 13.7 lakhs, and the total operating cost or total variable cost turns out to be rupees 1.1746 into 10 to power 6 or rupees 11.746 lakhs. So, that completes the solution to the problem. Now, we shall see a theoretical problem related to absorption. We often use Kremser's equation for obtaining the number of plates in an absorption tower. However, Kremser's equation has its own limitation. Okay. So, we shall see as under what circumstances we can use Kremser's equation, or in other words we shall derive a criteria for use of Kremser's equation. So, that is our next problem. We have to prove that the criterion for applicability of Kremser's equation is given by the following expression. Y in into 1 plus 2 into A21 minus A12 into or a plus delta H V square divided by R Cp TL square bracket complete into Gs by Ls, and this has to be less than or equal to 0.1. So, this is the criteria. Now, let us see various notation. Y in is the mole ratio of solute in the inlet gas stream. A12 and A21 are the Margulis constants of solute and solvent at infinite dilution. Then Cp is the heat capacity of liquid, TL is the temperature of liquid, delta Hv is the heat of vaporization, and Gs and Ls are the flow rates of gas and liquid. Molar flow rates of gas and liquid. So, we have to develop this criteria. We are given the Margulis equation for activity coefficient. Margulis equation is ln gamma 1 denotes solute, 2 denotes solvent, x2 square into A12 plus 2x1 into A21 minus A12 and gamma naught, that is activity coefficient at infinite dilution, is exponential A12. Okay. So, we start our solution. We first draw a simple schematic of an absorption tower. A tower having n plates, inlet flow rate of gas Gs with mole ratio x in, outlet flow rate of Gs, carrier gas, not the total gas flow rate, it is the carrier gas. Gs into x out is the mole ratio in the outgoing gas, L is the total flow rate that comes in, carrier, so solvent flow rate, then x in, oh sorry, here we are using notation y for gas mole fractions. So, the solute mole ratio in the incoming gas is y in, capital Y in, the solute mole ratio in the outgoing gas is capital Y out. So, please make this change. For liquid we are using the letter x for mole ratio, x in is the mole ratio of solute in the incoming liquid and x out is the mole ratio of solute in outgoing liquid. Now, if we write a balance for the top of the tower, writing mole balance at the tower top, which means we include the first, only the first two plates, okay. Then we can write a simple balance Gs into y n minus 1 minus y out is equal to Ls into x n minus x in. This is the balance for plate n. Okay. Now, the equilibrium relation is given by Pt into y is equal to gamma into P naught into x. Pt is the total pressure of the tower, y is the mole fraction of solute in gas, x is the mole fraction of solute in liquid, gamma is the activity coefficient. We are not taking into account the fugacity coefficient here because the pressure is relatively small. So, you can take phi, the fugacity coefficient as 1, okay, and P naught is the vapor pressure absolute. Okay. Now, Kremser's equation will apply if both operating line and equilibrium line or equilibrium curve, I would say, are straight. We write the equilibrium relation, we rearrange the equilibrium relation that we have written as y is equal to gamma P naught by Pt into x, and this particular thing gamma P naught by Pt in bracket is denoted by letter m. So, y is equal to mx is our equilibrium relation. The relation between mole ratio and mole fraction Mole fraction denoted by small y, mole ratio denoted by capital Y is this. Small y is equal to capital Y divided by 1 plus capital Y, and this is equal to gamma p naught by pt into x, then x also written in terms of capital X. And then we rearrange this. And now what we have here is the modified m for mole ratio. When equilibrium relation is defined in terms of mole ratio, the m, the constant of the equilibrium, is gamma p naught by pt into 1 plus y divided by 1 plus x. Now, to see the variation in m, we expand it in a Taylor series around conditions of infinite dilution. As long as m remains constant, the equilibrium curve will be a line and Kramser's equation will apply. So, we shall see as what are the criteria for constancy of m, okay? And conditions of infinite dilution are y equal to 0, capital Y equal to 0, capital X equal to 0, and T equal to TL, the inlet temperature of liquid. And at these conditions, at the conditions of infinite dilution, we write m is equal to m naught, which is equal to gamma naught p naught naught by pt, where the subscript naught denotes standard condition or reference condition. So, we now expand the Taylor series. M is a function of 3 variables, capital X, capital Y and T. And now evaluate the partial differentials of that appear in this expansion. First, dou m by dou y at y equal to 0, x equal to 0, t equal to TL is equal to dou by dou capital Y of gamma p naught by pt into 1 plus y divided by 1 plus x. This turns out to be gamma p naught by pt into 1 divided by 1 plus x at x equal to 0, y equal to 0, t equal to TL, and this is essentially m naught. Then similarly the second derivative, dou m by dou x. at y equal to 0, x equal to 0, t equal to TL. Then here we substitute for m, and then we get this. Now here the activity coefficient is also a function of x, so we take variation of that as well. Now dou gamma by dou capital X can be written using chain rule as dou gamma by dou small x into dou capital X, sorry, dou small x and dou capital X, and then this is essentially equal to 1, the second thing. So dou gamma by dou small x. Now activity coefficient is given by Margulis equation. And then we try to develop an expression for dou gamma by dou x using that. Margulis equation is ln gamma 1 x2 square a12 plus 2x1 into a21 minus a12, then taking derivative with respect to x. Now here we have to take with respect to x1 because 1 denotes solute. Here we write x2 square as x1 1 minus x1 square. So now simple expansion and simplification. And then we take 1 minus x1 common. Now we are evaluating this integral at conditions of infinite dilution. So we substitute x1 equal to 0. And then we get dou gamma 1 by dou x is equal to at x equal to 0, y equal to 0, t equal to TL, gamma 1 naught minus 2 a12 plus 2 into a21 minus a12. This is equal to, after simplification we can take this, and now we do not write one subscript here because we have only one solute. So the subscript 1 we drop and just write 2 gamma naught into a21 minus 2 a12. Okay. And now substituting for dou gamma 1 by dou x in the expression for dou m by dou x, we get dou m by dou x at y equal to 0, x equal to 0, t equal to TL is equal to minus m naught minus 2 m naught into 2 times a12 plus a21. Okay. So, that completes the second partial derivative. Now, we have to evaluate the third partial derivative of m with respect to t. Okay. Now, for evaluating that partial derivative, we consider that both gamma and P naught are function of temperature. However, among the two, gamma is a weak function of temperature. For gas mixtures containing dilute concentrations of solute, the amount of heat that is liberated with dissolution of solute in the liquid is relatively small. So, the temperature of the liquid does not vary by a large number, maybe by 5 or 10 degrees, and for that small variation of temperature, gamma can be assumed to be constant. So, assuming knowing that gamma is a weak function of temperature, we assume that it remains constant. Now, for variation of P naught, vapor pressure with respect to temperature, we make use of Clapeyron equation. P naught divided by P naught naught, that is at reference condition, is equal to exponential minus delta HV by R, the heat of vaporization, into 1 by T minus 1 by TL. Okay. So, reference temperature we take as the inlet temperature of liquid. And now, with this we try to find out dou m by dou T. Dou m by dou T is dou by dou T of gamma P naught by Pt into 1 plus y divided by 1 plus x at conditions x equal to 0, y equal to 0, t equal to TL, and then everything comes out. What we get is gamma Pt, gamma by Pt into dou P naught by dou T at condition of x equal to 0, y equal to 0, t equal to TL. Now, dou by dou T of ln P naught by P naught naught, we just take the derivative of the Clapeyron equation, is dou by dou T of minus delta HV by R into 1 by T minus 1 by TL, and then this is delta HV by RT square at x equal to 0, y equal to 0, t equal to TL, or delta HV by R TL square, and the right hand side is nothing but 1 by P naught into dou P naught by dou T, and this implies that dou P naught by dou T is equal to P naught into delta HV by R TL square, and that we put here. So, dou m by dou T is gamma by Pt into P naught into delta HV by R TL square, or gamma P naught by Pt into delta HV by R TL square. or simply m naught into delta HV by RTL square. Now, we substitute all partial derivatives. We now have a relationship of all variation of m with respect to capital X, capital Y and capital T, or the temperature. So, substituting partial derivatives in expression for m, we get m is equal to m naught into 1 plus y minus x minus 2 to 2a12 minus a21. Here we take the negative sign outside and adjust it inside the bracket into x plus delta HV by RTL square into T minus T. This bracket complete. Okay. Now, for maximum possible difference between m, the slope of equilibrium curve at any given condition, and m naught, which is the reference condition, we have to consider maximum values of all variables on which m depends. So, we take y is equal to y in, x is equal to x out and t is equal to t out. These are the maximum values. The mole ratio of solute in gas is maximum at inlet condition. The mole ratio of solute in liquid is maximum at outlet condition, and temperature of the liquid is maximum or is mostly different at exit conditions. So, then m is equal to m naught into 1 plus y in. We substitute for x and y these values minus now we take this as common, 1 plus y in plus 2 into a21 minus 2a12 into x out plus delta HV by RTL square into T out minus TL. Now, if the absorber is designed for 99% recovery, then Gs into Y in is same as Ls into X out. Most of the solute in incoming gas is absorbed in liquid, and then the heat that is released during this absorption, heat released with solute dissolution, appears only as a sensible heat change in the liquid. Gs into Y in into delta HV is equal to Cp into Ls into T out minus TL. And then we substitute for T out for T out minus T L, we substitute G S into Y in into delta H V by C P into L S here for this, and for X out we substitute this G S into Y in by L S. Heat that is released during this absorption, heat released with solute dissolution appears only as a sensible heat change in the liquid. So, G S into Y in into delta H V is equal to C P into L S into T out minus T L. And then we substitute for T out minus T L, we substitute G S into Y in into delta H V by C P into L S here for this, and for X out we substitute this G S into Y in by L S. And with these substitutions, we get M is equal to M naught into 1 plus Y in into the bracket 2 into A21 minus 2A12 plus delta HV square divided by R Cp TL square bracket complete into Gs by Ls. Okay. Or we take M by M naught equal to 1 plus Y in 2 into A21 minus 2A12 plus delta HV square by R Cp TL square or we rewrite this. Okay. M is equal to M by M naught is equal to 1 plus Y in into 1 plus 2 into A21 minus 2A12 plus delta HV square by R Cp TL square bracket complete into Gs by Ls. Okay. Now, M will not differ from m naught if the second term on right hand side is small in number, okay, or numerical value or negligible. Okay. And therefore, we can say that Kremser's equation will apply. If the numerical value of the second term on the right hand side is less than or equal to 0.1, that means m will not differ by more than 10% from m naught, and therefore, the equilibrium curve will be essentially a straight line. So, that point we note Kremser equation will thus apply if the numerical value of second term on RHS is less than 0.1, which means that m will not vary more than 10% than m naught, and hence the equilibrium curve will be a straight line. And thus, we prove that Kremser's equation will apply. Prove that Kremser's equation applies when y in into 1 plus 2 into A21 minus 2A12 plus delta HV square by R CPTL square into GS by LS is less than or equal to 0.1, and that is the solution. So, today we have seen two problems related to design of absorption column. In the next tutorial, we shall see problems related to distillation.